you. Thank you for the nice introduction, and also thanks for being here. It's good to see old friends and colleagues, people I've known for many years and working in the field. I came to NCAR originally from Canada, so initially did a lot of work on atmospheric and climate models, but also looking at solvers. So I think the previous speaker's talk is a very good introduction to this talk, and I will actually have some updates on performance of the solvers, but also I'd like to talk about convergence, stopping criteria, a number of points that were brought up by the previous speaker. This is very much a collaborative effort, but I want to say this really has been led by Kasia and myself at NREL. We've been investigating Krylov methods, Krylov solvers, and finding ways to make them far more scalable, but also, and Kasia presented here last year, looking at implementations on GPUs. The solver technology is making its way into Hyper, so we've been collaborating with the Hyper team at Lawrence Livermore. And what I'll present today also includes work over the summer with Sandia National Lab. So we have now explored pipelined and SStep Krylov methods with Mark Homan and Ishi Yamazaki and the team, the Trillanos solver stack team down at Sandia. We're also collaborating very closely with Julian Langeau, so I think I really want to express my gratitude to Julian. He's the chairman of mathematics at CU Denver. His PhD in France was also on Krylov methods, and really his insights, I think, have led to this work. His PhD student, Daniel, is now looking at eigenvalue problems based on what you'll see today. It's a long introduction, but I really want to acknowledge everybody involved. Okay, so what have we been doing, or what could possibly be new in Krylov methods after all these many years? And what I'd like to say is that a few things were missed over the 100-year history of Gramschmidt as an algorithm, and then through the work of Lanchos and the developments in the 50s and 60s leading up to the use of conjugate gradients and Krylov method, eventually GMRes in the 80s, several things were missed. And in particular, we've been doing too many global reductions. I want to put that out there as the basis for our work in the talk, is that really we don't need to do as many reductions as the algorithms as they're found in textbooks would suggest. So that's really a good overview, or the basic idea of the talk. What we've implemented over the past year are two variants of GMRes, but they're not the GMRes that you've seen, for example, in Yosef Saad's original paper, or in his text and all the work since. What we've done basically is go back and recognize that there's a different form of both modified Gramschmidt and also of the classical Gramschmidt algorithm, and I'll get into the details of that. Our goal is to simulate airflow over wind turbines. That's ultimately the goal of our work. It's an ECP Exascale project, and so we'll present results on Summit on some of the fast computers that people have mentioned already today, on Cori at NERSC and also Summit, and we have a GPU-based machine at NREL as well. If time permits, I'd like to mention some of the other smooth components of the solver stacks. In particular, if you look at the total package, and the previous speaker mentioned multigrid, and in our case, we're looking at algebraic multigrid, there are setup costs that are certainly high, but the really basic time-consuming part of algebraic multigrid would be the smoother at each level in the V-cycle hierarchy. So we're also trying to improve that, and in particular, move away from lower triangular solvers and instead look at matrix multiply-based smoothers because they're so much faster on a GPU. Okay, well that gives some context. Want to move a little faster, but basically the core iterative solver technology, if you will, that's evolved and is used in weather models and the major DOE solver stacks. These are Krylov methods, and GMRes is perhaps the most widely used, and the reason for that is it can handle non-symmetric matrices. Conjugate gradients, as it evolved originally, is for symmetric matrices, and it's basically the Lanczos algorithm for eigenvalues is equivalent to conjugate gradients. I'll mostly talk about GMRes, but some of the conclusions also apply to conjugate gradient algorithms and also pipelined conjugate gradient algorithms, but time won't permit going into that. Okay, so what is a Krylov method? Well, it's basically we're trying to solve AX equals B, a system of equations. We take the residual and we project it onto a certain subspace, a Krylov subspace, Km, and in effect we're powering up A. Each iteration of the solver is a matrix multiplication, and also to accelerate these methods we need a preconditioner. An important distinction is how many, between different variants of the algorithm, is how many Krylov vectors do we orthogonalize within any iteration or at any step of the GMRes. So plain vanilla GMRes would just orthogonalize one vector at a time, and it's orthogonalization because in essence GMRes is computing the QR factorization, or an orthogonal factorization of a matrix that's growing, R0 AVM, at every iteration of the algorithm. And we're doing a least squares approximation of X at every step. So the Trillanos GMRes has the option of orthogonalizing vectors in batches of size S. So that's an SStep Krylov method. And that was known historically back in the 90s, or even before. Kim and Chronopoulos did a lot of work on SStep methods, but Mark Homan, who we've collaborated with, has extended, or really built stable SStep Krylov methods, or an SStep GMRes that's stabilized. So I'll present most of the results, if I can get to them, are related to the work that we've done with Mark and the team at Sandia to extend the work we've done recently from just one orthogonalization step at a time to SStep methods. Well, what I started out by saying was, well, what's new? What could possibly be new in Krylov methods? Well, it's the following theorem or statement, namely, you only need to do one global reduction per column or per iteration of any GMRes or Krylov method to achieve a stable, and by stable we mean a sufficient orthogonality such that GMRes or a Krylov method can converge. So stability in this context, and the previous presenter was getting or starting to address this notion of, well, how orthogonal do the Krylov vectors need to be in order to achieve a given level of accuracy? And the answer to that is that you need order machine precision condition number of A orthogonality to achieve the maximum or minimum possible error that GMRes could achieve. I'm not really saying the lowest error, which is not the relative residual, but rather the backward error, is achieved if the Krylov vectors are machine precision times condition number of the matrix orthogonal. Okay, so how do we do that? How do we go back and look at the original algorithms that are about 100 years old? What can we do or discover about them that would allow us to do less communication? Well, it turns out that the modified Gramschmidt algorithm, if you just picked up a textbook, you'd see that the projection step is carried out such that there are a quadratic number of inner products because of applying this projector one vector at a time in the inner loop of Gramschmidt, or modified Gramschmidt. So that implies a quadratically increasing amount of communication. That can be completely eliminated by recognizing that, in fact, you can write the projector as what's referred to as a compact Y representation. And this matrix T is triangular, and it's actually lower triangular. And so then modified Gram-Schmidt becomes basically a lower triangular solver. Now, what's new over the past summer, again, even beyond that, is with classical Gram-Schmidt, well, it's known that we need to reorthogonalize the vectors, apply the algorithm twice in order to recover machine precision orthogonality. Well, that's not necessarily true. In fact, there's a way of formulating the projector so that in one communication step, you can achieve machine precision orthogonality, and this is how it's done. In particular, the projector has a recursive form. It also involves a lower triangular matrix, and it still has two steps, but it's not an iteration. It's formed as a correction. So I'll get into the details of what I mean by that. But here's modified Gram-Schmidt. You no longer see an inner loop with many, or a quadratically increasing number of inner products. Instead, there's a lower triangular solve. And Kasia has presented this, and we presented this over the past year. So this has been well studied, but also the backward stability of the algorithm we've also studied. And by that we mean the representation error, or how close is the factorization to the original matrix, and the backward stability analysis of Aki Bjork, this 1967 paper. So in fact, these new forms of modified and classical Gram-Schmidt still exhibit the same backward stability properties as the original algorithms. So here's GMRes. It's not the GMRes you've seen before. It's basically taking that lower triangular solve and embedding it in step 13 right here. There's a couple of scaling steps as well, but what is important about, or what are we driving at with this formulation of GMRes? It's namely that the global communication is merged into one operation. So we have tall and skinny matrix vector products and a norm. That can all be merged into one blast of an MPI all reduce. And yet this has the same numerical stability properties as the original GMRes. So basically it's global reduce, scale the vectors for the Arnoldi QR, do the lower triangular solve, do a projection, you're done. And so this modified Gram-Schmidt GMRes is numerically equivalent to what you'd find in Saad's original paper, but it's way more scalable. And that's the rest of the talk. I'll try and demonstrate how much more scalable it is. A quick aside comment is, again, picking up on what the previous speaker mentioned, the notion of, well, where do we stop? What is an appropriate stopping criteria for an iterative solver? It's not necessarily, it's not the relative error. And I can show why. Basically, the relative error can stall out at the point where the orthogonality of the Krylov vectors is lost. And this is work of my supervisor, Chris Page, along with Rosloznik and Strakos in Prague. Not only did they establish the backward stability of modified Gram-Schmidt GMRes, but they've also gone back to work in the 60s and basically recommended that the norm-wise backward error is the better stopping criteria. And here's a plot of why that's the case. This is a very ill-conditioned matrix from Anne Greenbaum in Seattle, University of Washington. And it shows the magenta curve is the loss of orthogonality. It's basically a metric. The that's equivalent to the norm of I minus QQ transpose. So as this increases to 1, the relative residual stalls. Okay, this is the stopping criteria that most solver packages that we're all using. It's really not reliable. What we should be using is the normalized backward error, which hits machine precision the moment orthogonality of the vectors is lost, and actually the vectors lose linear independence. Okay. So that being said, we'll get back to that in the context of SStep GMRes. But I want to present Kašia's scaling results, in particular comparing hyper versus the new variants of GMRes that we're now putting into hyper. And in particular, this is hyper out of the box. It's their GPU implementation, but it's still using the quadratically increasing number of inner products, and it's stalling out. The strong scaling is basically plateauing. And whereas with the implementation that Kašia has put together, the strong scaling is much improved. It's about the bend over point or saturation is 4 times further out, and the code is about 3 times faster. And we can really see this in the communication. So we really want to emphasize this is the time spent in the Gramschmidt orthogonalization, and the communication is essentially flat. Whereas in the traditional approach, it's growing quadratically. So this solves the problem of reductions and scaling for Krylov methods, basically. What we're saying is we don't need to do as many reductions. And here's a benchmark case. We call this the McAllister wind tunnel, McAllister blade test. It's one of our benchmark cases for the NALU wind CF incompressible Navier-Stokes code. So most of our results, again with Sandia, and our results are performance for this benchmark problem. So just showing that a GMRes AMG preconditioner pressure solver converges in about 8 iterations. We also have a pressure projection scheme or solver projection scheme that can reduce the number of iterations if we use previous initial guesses. And we've given a couple of talks about that. I won't present that here due to time, which I'm running out of. But the projection scheme is also based on classical Gramschmidt. Okay, so classical Gramschmidt, every textbook that you've ever read on numerical linear algebra would say, well, classical Gramschmidt, you have to run the algorithm twice. You have to reorthogonalize and iterate. So there are 3 synchronization steps here. There's 2 global sinks, and then a final global sink, a 3rd global sink for the norm. We don't need to do that anymore. We can reformulate classical Gramschmidt as a type of recursion where the projector is written in I call it a feed-forward sort of form. I like to quote the Rolling Stones. This is, you can't always get what you want, but sometimes if you try, you can get what you need. Namely, that if you insert the future computation for the reorthogonalization directly into the projector, out pops out this triangular matrix T again. And indeed, if you follow the development through, there are 2 correction terms that reestablish orthogonality. So now we can do classical Gram-Schmidt with 1 global reduction. We don't need to iterate. And you can see it in this slide. So we do tall and skinny matrix vector product, and then we do the corrections, and the correction inner products are purely local to each rank. So there's quite a bit going on here, but basically it's do tall and skinny, do the corrections, then do part of the projection, and lag, and this if you look at parallel pipelined algorithms, lagging of both the reorthogonalization step and the norm allow us to do that. So we do part of the projection and then we complete it in then basically the next go round. Here's some plots that Kasia put together showing that indeed we achieve machine level orthogonality. The other plots are, this is of the representation or backward error. The existing published algorithms don't achieve this. So there are published algorithms in the literature that are basically not achieving machine level backwards error, and they're also not achieving machine level orthogonality. Orthogonality is everything for Krylov methods, and if you can do that, then eigenvalue computations become much more accurate and efficient, and you basically have a stable algorithm. So orthogonality is directly related to the stability of the algorithms. Okay, I want to finish up, I hope I'm not going over time. I want to finish up with the SStep methods from Mark Homan and the team at Sandia. So as I said, in an SStep GMRes, you're doing a block of S Krylov vectors. And this is showing how that implementation improves the time per solution just in the pressure solve. I better finish up. This is showing convergence curves for the Laplace problem and also the loss of orthogonality on the bottom. Just a couple more slides. This is the same sort of plot. It's convergence versus loss of orthogonality, and showing classical Gramschmidt, modified Gramschmidt, and just one pass of classical. So the main part of the story, and these are the last two slides, are that the one reduction allows us to speed up these algorithms by a factor of 2 or 7 times. So in the case of modified Gramschmidt, for blocks of S Krylov vectors, we're getting almost a 10 times speed up per iteration. And I'll just end on this slide. This is comparing the different SStep versus the single reduce modified Gramschmidt on Summit, and the single reduce is the most scalable of all the algorithms. So even though SStep allows pipelining and merging of operations, the single reduce leads to the most scalable Krylov solver, we think, to date. So I'll stop there. Sorry for going long.
We